to try to do something more interesting. Now, I'll say in advance, this is introductory stuff. Eventually, if I, talk fast enough, I'll get to things, somewhere along the line that, all of you haven't seen before. But the only way to get there is just to make sure we build up a common understanding. Before I really start generalizing things, I should just spend a minute talking about this preliminary issue, which is picking a loss function. So we're just, for the time being, thinking of linear function learning, where we're just learning a hyperplane, predicting a scalar output. And of course, there's a whole host of ways we could imagine assessing output prediction errors. In fact, I don't even feel that dogmatic about these, but here are the sort of the usual suspects. We have absolute error, that's the one I started with. We have everybody's favorite squared error. We have like p-norm like errors. I probably should have put an absolute value on that, and so on. Maybe I should say a word about a squared error. Normally, in a course, what I'll do is spend a lecture or two talking about squared error only. Why this fixation on squared error, you ask yourself? Many of you may know this, but in many respects, squared error is like looking under the light post. Why do I say this? If you just square this prediction error and you look at the computational problem, it's a massive improvement because we go from a linear program required to solve something like this to solving a single linear system to solve squared error. So it's computationally expedient. And moreover, when you're in real-time like settings, say like signal processing, although you can solve LPs pretty fast, but still they don't really like that idea. They want to have fast linear solves, and in fact, even faster than linear solves, they want to do things like fast Fourier transforms and so on. Okay, so that's one reason why squared error is popular. The other, maybe the only real principled reason why you would use squared error would be if you're making Gaussianity assumptions, right? If you're really, fixated on Gaussian noise modeling, and you look at things like, maximum likelihood or map or Bayes, which we'll see eventually, this would wind up being like the optimum choice. This is the, minus log likelihood, okay? But, come on, how Gaussian are really the types of things we're interested in doing? Not very, so that's not a particularly good reason. The other most compelling, in my view, reason to do squared error is that for free, you get Euclidean geometry. And beauty ensues. Right away, you can start looking at all your functions as vectors in a Euclidean space. Suddenly, your learning problem just becomes a projection operator from some function onto the space that you can represent. That projection has a Pythagorean theorem where the sum of this, the mean squared prediction error decomposes into a sum of two mean squared prediction errors. One is the bias, one is the variance. All this wonderful theory, all this wonderful geometry, all this stuff follows. Okay. That's just great, but the truth is, it's risky because squared error, as you probably are aware of, is incredibly non-robust, right? If you have an outlier training point, what you're doing is you're taking that one larger error and you're squaring it relative to the other errors, and you're going to chase it, okay? L1, or absolute error, has a huge advantage there, right? Because it's a lot more robust. It doesn't chase outliers to the same degree as L2, okay? In fact, between L1 and L2, there's a whole space, LP, from 1 to infinity, right? You think of 2 as being closer to 1 than infinity, but of course, when you're talking LP norms, 2 is right between 1 and infinity. And so L2 is about halfway to being as non-robust as you could possibly be. Okay. Now, when you start looking at things in terms of p-norms, you would really want to be, if you are interested in robustness, you'd really want to reduce p as far as possible. Well, it turns out that p equals 1 is as small as you can go and maintain convexity. Okay. Once you go beyond p equals 1, then the loss function becomes more robust, but it's non-convex, and we're going to lose tractability. Okay. So this is usually your sort of best compromise choice. All right. Anyway, we don't even have to restrict attention to these. It could be, we could be up against more interesting things like what if the things we're predicting happen to be probabilities? Well, then none of these loss functions make sense. And other loss functions like entropy-based loss functions, cross-entropy, KL divergence, and so on are going to make a lot more sense. Okay. I'm not going to do much about loss functions right. Oh, is that a question? Wow. Sorry, you're going to have to yell. I could, but I'm not gonna. I don't have any slides. So the easiest way to see it would be to write the definition of the norm, right? So if I have a vector, the norm. Oh, by robust. So, OK, so just have a look at the diagram. OK, so this is a 0 you can't see, right? So down below is, say, the difference y hat minus y. OK, and what's being plotted here is the error measure that's associated, right? So if y hat minus y is 0, you get 0 error, and that's true in all of these cases. OK, what's happening here is that as that error difference gets bigger, this is how fast your error measure is growing. OK, so L1 is just linearly. All right, L2 it's growing quadratically. So this leads to, why does this lead to non-robust behavior? Because as you get an outlier, that's the thing with the big error over there, right? And you've squared it, so that error is going to dominate, and you're going to pull the model over to make that error smaller and sacrifice the smaller errors, okay? Now, when you go below L1, what's going to happen is you'll start to get, think of like square root, 1/2, right? You're going to start to get something that looks like these 2 square roots, okay? Well, that's going to be even more robust because as the error grows, it's actually going to start to give up, right? It's going to have less and less and less influence as the data point moves further away. All the way to looking at functions like this, right? So this would be sort of a toy version of a robust loss where we literally clip it. So we say that the maximum error you can get for a point grows quadratically or whatever, right? And then it hits some maximum value, and after that value, that's it, right? I don't care anymore. It's not any worse, okay? This is, in some sense, at least, asymptotically as robust as you could get. Yeah. Yeah. OK. What was I going to say about loss functions? I'm going to come back to this in more depth tomorrow. And in tomorrow, I'm going to actually try to show you how you can derive loss functions from other considerations. In particular, when we start imposing nonlinearities, you have to be very careful about how you engineer the loss functions to maintain tractability. Okay? For today, I'm just going to say, pick a loss function, make it convex. Okay? And then we'll just go from there. Convexity is an issue I'm sure you'll hear a lot about over the next 2 weeks, right? But I might as well just say a little bit about it to start. We all know what a convex function is, at least to look at a picture. It's bowed upward. The technical definition is this thing that looks worse than it is. It's basically just seeing that a convex function is a function where if you take weighted averages of 2 points, the function at the mean is smaller than the mean of the function. Or, you draw this chord and it's above the function everywhere. OK. Why the fixation on convexity? Well, actually, convexity per se is not necessarily of interest unless you're into convex analysis. But it's empowering, especially when we're approaching most of these problems as optimization problems. The key thing about convexity is that it is a sufficient, perhaps not necessary, but a sufficient condition to generally give us tractable optimization problems. For the following reason: if you have a convex loss function, say, and you find any local minimizer of that function, it's guaranteed to be a global minimizer. So we can just pursue simple myopic local optimization strategies, find some local solution, and declare victory. Okay? Properties here I won't go into. So I'll just say sort of generally, convex losses are going to yield tractable problems for us, and non-convex losses are generally going to result in NP hard or worse optimization problems for us. Of course, those are wildly general statements, and they're not always going to be true, okay? And we will see some exceptions, like convex problems that are intractable, non-convex problems that are tractable, okay? But those are like the special cases. Just some other background issue when picking a loss function is smoothness. So I'm not too fixated on smooth or non-smooth, but some people are. All of the, say, LP losses are going to be smooth. That is differentiable everywhere for p strictly bigger than 1. And smooth is nice in an optimization setting, right? Because then you've got Newton's algorithm. And if the Hessian's too big, then you've got LBFGS, right? You've got super linear, convergent, well understood, already coded algorithms for solving these problems, okay? When you go from smooth to non-smooth, in optimization, this is a fairly significant step, and sort of the reliable, computational approaches to tackling non-smooth problems kind of, have to address issues that are not present in the smooth case. So I'm not trying to say it's a trivial step, but the truth is non-smooth optimizers work fairly well. In fact, the best ones kind of cheat and pretend it's smooth and then patch it up. For me, convexity seems more important because that's going to yield tractability. We're not usually going to lose tractability just because we've introduced some non-differentiable points. Okay? So let's not be afraid of non-smoothness. But I'm not going to sort of dwell a lot on the technical details of optimization. I expect that other lecturers might through the following 2 weeks. OK, last consideration for loss is robust. I guess I talked about that already. So I won't say more about it. Robustness would be good. Another thing I've sort of mentioned already is that I'm going to assume for the most part that the losses we have, or we're thinking about, decompose additively over the training examples, which is sort of tacitly assuming that we're in an IID setting. We've got a fixed stationary distribution. We're drawing data from that distribution. We're learning a model from that data. And then we're applying that model to data drawn from the same distribution. Okay? We're not worried about non-stationarity or drift or adversaries or things like that, although those are interesting issues. There are interesting non-IID losses like F-measure and some classification settings that are worth investigating. I'm just going to sweep this issue under the rug and generally assume IID. Until the end of tomorrow, at some point, I can show how some of the structure prediction ideas can be used to fake non-IID-like losses. Okay. All right, so I'm just going to assume we pick some loss that we're happy with, call it L, and move on. Okay, some convex loss. Okay. Generalizing the domain representation. So we've got a linear function. We've fixed our hypothesis space. We're still doing empirical error minimization. And we've picked a loss, whatever your favorite is. Okay? How are we going to get nonlinear and sort of have more flexible modeling that we can apply in more domains? Well, we're going to start by just generalizing the input, the representation of the inputs. OK, idea one, this is not deep, right? And you're all probably aware of it, but let's just be clear, everyone is aware of it. Cheap trick number one is that if I really want nonlinear models to learn a map on the data, all I have to do is fix a basis. That is, I just have to choose some fixed set of basis functions, say call each one phi1 to phi l. Okay, where each basis function is some, say, nonlinear function of the original data x, however that original data was revealed to you. Okay, all we have to do is take the data and expand it out into some feature representation. Okay. So mechanically, the approach is it doesn't change anything. In fact, so if I have my data and then I just have some pre-processing step that takes, say, each row vector. So I'm going to assume by convention that examples are like the input examples are row vectors in a matrix X. Okay. So the pre-processing step is I just take a row vector and then I apply the full row. To the first, I apply the first feature function to the full row, second feature function, and so on. So I map the original vector into some new vector in some new representation. Okay. Pre-processing step. So I take my original matrix X, I map it to a new matrix, say phi. Then what do? Well, I don't have to worry about anything. I just apply the same learning approach. I just learned some weight vector W, but over the phi representation. Okay? Same problem before. In fact, you call the same code, right? You just solve for an optimal weight vector given whatever input matrix you care to use. Okay? What else? Oh, in this case, what we would interpret the weights as, you might interpret them as like coefficients on these bases. Okay? Anyway, it's an obvious idea. It's a really easy idea. I'll just give you the obvious examples. So if you're teaching your introductory machine learning course to undergrads, right, this is where you start. Consider polynomials. So usually what I'll do is I'll show, like, say, linear function learning and say, OK, can you compute for me, say, the minimum absolute error, fourth order polynomial fit to data? And everyone goes, but it's trivial, right? If you want to fit polynomial functions to data, polynomials are just generalized linear functions. All you have to do is take your original, say, scalar observation and just map it out into a new feature representation, where the new feature representation is basically the 0th power, 1st, 2nd, blah, 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 up to some dth power of that data. right? So you map a scalar into a feature vector, do that for all your data, and now you just have a matrix, you hand it to your solver, it's going to learn a vector of coefficients over those terms, right? Least, and the loss function, doesn't affect anything. Least squares, absolute error, LP error, what have you, okay? If we've picked a convex loss, it's still a convex problem to solve for those weights, and we get some new predictor, which I forgot to emphasize before, is a nonlinear predictor, right? So once we've learned the weight vector, if I get some new example x and I want to make a prediction on that example x, I just first do the same pre-processing step, expand that new example x out into its feature representation, take the inner product with the weights that we learned on the training data, get your prediction, okay? Couldn't be easier. Oh, yeah, so, here's my, third order fit to that data. Okay. I don't have to rewrite the linear program, right? It's just same linear program, okay. Now, let me just sort of go through a few sort of standard examples people learn about. I won't dwell on these. You get the idea. But this idea, of course, is predominant. If you're an applied sort of analysis area, say like image processing, you can look at a lot of what's being done as feature engineering. That is, you take an image. What are the important salient things that you need to extract from that image? Those important salient things are like features of that image, say like an edge or a corner, right? And then you re-express the image in some new feature representation, okay? If you're into signal processing, a common set of features are, for example, trigonometric basis functions, right? Here, you can set things up happily if you literally have scalar data and it's evenly spaced, so like signal processing, like evenly sampled, and then you set up the right choice of orthogonal trigonometric bases, well, then you get something really nice. In fact, you get a square matrix, okay? And you can get a square matrix where the columns of this matrix are guaranteed to be orthonormal columns. And if you happen to be doing least squared loss, your whole fitting problem, your whole training problem, reduces to a single matrix vector multiply, right? And in fact, that single matrix vector multiply in this case would wind up being like a discrete version of a Fourier transform, which, by the way, is still too slow for signal processing, and you would want to exploit the structure in this matrix to reduce an n-cubed algorithm down to an n log n algorithm. Okay? There's one instantiation of bases. You can do things with splines. If you want piecewise cubic functions through data, the easiest way to think of it is just to have a bunch of basis functions. So I take my scalar observation and I map it out into a feature representation of piecewise cubic functions, constant, linear, quadratic, cubic, and then a bunch of these piecewise cubics. So here I mean x1 is some like naught point, and then x minus x1 plus is forced to be 0. So if it goes negative, we clip it to 0, and then we just have the cubic there, okay? So piecewise cubic. And then we just set up a bunch of these bases that are piecewise cubics defined at a bunch of different knot points. And then you can learn basically easily, just by feature expansion, piecewise cubic fits of data, for example. Okay? Now, normally splines are associated with interpolation. We're not really so interested in interpolating data, in particular if there's noise. But you don't have to use splines to interpolate. You could actually even use splines to just approximate data. Okay? Here's an oldie but a goodie. I feel kind of really, really old every time I put up a diagram like that. But, I swear these things are coming back. So this is what we used to call a neural network, okay? So back in the day, we drew these bow diagrams. And what they would mean is this is our input feature vector, okay? And then we would have these hidden units. But each hidden unit is basically a basis function. Okay? It's a basis function that happens to be parameterized by some auxiliary parameters, say mu k for basis function k. Okay? And it's some nonlinear function of the inputs, parameterized somehow. Okay? And so we set up this layer of hidden units. It's basically just a set of features, feature functions. The output layer is the linear model up here. Okay? And so if we fix the bottom layer, we train the upper layer the same way as everything else. Okay? What's different here is that normally when we're doing, say, like a multi-layer network, say a 2-layer network, is that we're not just interested in training the output layer, but we're also interested in simultaneously training the input layer at the same time. This is interesting. It was interesting then, it's still interesting now, okay? This is learning the basis at the same time as learning the linear model on top of that basis, okay? That's hard. It's MP hard, okay? It's not good computationally, all right? But from a modeling perspective, this is kind of an exciting thing. Now, neural networks, I can't tell anymore, but I think they've kind of fallen out of, favor with the general, swept aside by support vector machines or something, but making their big comeback. What can I say about this? The biggest difference we'll see is that this is an intractable training architecture, which means it's really only handleable in the hands of an expert, okay? Here's a problem. If you want to do something fancy like this, and I'll get to like techniques that we're exploring now to do things like this, if you want to do something fancy like this and it's intractable, put yourself in the position of somebody in practice, right? They're not machine learning researchers. They're not optimization researchers. They download code on the web. They model their little problem, so they'll set up their little architecture, okay? On their data, they hit solve, okay? Thing comes back with a solution. Well, it's intractable. What it's come back with is some local solution it could find, okay? Great, they say. And then they take their holdout, test data, and then they evaluate their predictor, and they go, ugh, that's bad. Well, now you got a problem, okay? And this is what machine learning was like 20 years ago. The problem at this point is you have a global optimization problem, okay? Did you set up a bad architecture? You have no idea. All you know is that one solution that thing found isn't good enough, okay? What are you going to do now? Well, you've got two options. You can go and start fiddling around with the optimizer, like, ooh, restarts. Maybe we initialize better. Maybe we just try a lot of restarts. Maybe we should do, ooh, simulated annealing. Genetic algorithms. You just go off the global optimization deep end, and you never come back, okay? But in the meantime, what's been forgotten is you forgot to think about the problem. Okay? Now contrast this with, okay, I haven't shown you support vector machines, but contrast this with a learning paradigm where you hit solve, and the thing that comes back is the answer. There is no debate, right? You download the code. If you download 2 sets of code, they give you the same answer. It's a global solution to this problem, okay? So you set up your fixed feature representation, you hit solve, you get the thing, you run it on data, and you're not happy. What do you do now? Well, you're not going to mess around with the solver, right? The solver people make their solvers, they all do the same thing. That's not your problem. Your problem is to look at the features that you fixed and discover that they're really bad, right? And so you think about your problem and how you're modeling the problem, and you improve the model and you make progress. This was a revolution. I mean, this really in practice is not a trivial thing. This is the difference between a technology that users can use and a technology that just researchers can keep in their research labs. I'm simplifying a bit, but you kind of get the idea, okay? So one of the goals of current research, you might interpret as trying to get these things to be more sort of user-friendly, okay? And I'm going to definitely show you some ideas about how to go about this. Thing number one that you should never do is never fix the number of features that you're going to optimize over. Feature selection is a killer, right? If I say you've got to do it with like 5 features, only 5, that's never a good idea, okay? There are better ideas than that, so I'll come back to that. Okay, anyway, neural networks would be one example of a feature expansion, okay? Sort of last idea, last idea generally for feature expansions sort of captures another family of approaches, which are, I guess what I just call local basis functions or similarity-based approaches. Right? So another way to have nonlinear re-representations of data is to reconceive of the data points, say the x vectors that you're seeing, in terms of their relationship to each other, almost like in a network. Okay? And what we're going to do here to start with is we don't start with a basis. What we're going to start with is some similarity function, kappa. Okay? And what kappa is going to do is it's going to take 2 arguments, so it's going to be 2 observations, and it's going to compute a similarity. Now, generally, the similarities that we compute, they don't have to be, but generally the ones we compute, say, will be some non-negative similarity. So big is good, small is bad, 0 is the worst. Okay? So here would be an example. The kappa function is like a similarity between some, say, fixed center, call that xj hat. So we fix some center, and then we get this response function around that center, say like a Gaussian or something, okay? And then what we're going to do is we're going to say, well, let's make features out of that. We're going to design, say, the jth feature function, which is a nonlinear function of the data, is simply going to be the similarity to one of the training points, okay? Pretty easy. And so what we're going to do is we're going to use the training points to fix the centers, and then we're going to plunk one of these basis functions on each of the centers, and then define a new re-representation of the data. So sorry, I don't have a matrix here, but if I had my original data matrix and I look at a row, my new feature representation of that data point is just a vector of similarities to all the other data. Reasonable. In fact, there's nothing to stop you from mixing any of these expansions. I could add splines, whatever, okay? You could even compose, as long as it's a fixed pre-processing step. And so it's the same game. We just expand out the training data. Then it's just a linear learning problem. We optimize the coefficients under whatever loss you're interested in. Most popular example being the unnormalized Gaussian. But, there are others. Little catch here. There's a little parameter here, which is the width parameter. That winds up playing a pretty huge role in how these things behave. I should say more about that in a bit. OK, so if we're going to use like local similarity, so I'm going to re-represent data in terms of a vector of similarities to other data. The most natural way to do this, of course, is just to make every data point a center. Now, the centers don't have to be data points, right? It could be just some set of points you pick somehow, cluster, whatever, OK? But sort of the simplest, cleanest way to do this is just to put a center on every training point, OK? Now, what's interesting about this is that, my original representation vector gets mapped out into a new feature vector, and the length of that new feature vector is exactly the same as the length of the data, right? And in fact, the new matrix that I create is a square matrix. Okay, it's a square matrix. I'll tellingly call it K, but anyway, it's just some square matrix. Okay. Now, if I have a square matrix and it happens to be full rank, and you're interested in minimizing any loss, it doesn't even have to be convex. You can do it with a single solve, right? Because you can get all of your prediction errors to 0 instantly by just solving this linear system for the weights. That is, you can do interpolation. Okay. So in fact, local basis functions are really sort of a standard way to think about interpolation models. In fact, you can even represent splines in this way with B-splines. Okay? And you can do interpolation. Now, interpolation is, it's probably not a good idea, right? If you're looking at real data with noise or even like model mismatches going on, you probably don't want to literally just solve. Okay? But you could. And you're guaranteed that this crazy nonlinear function you create is going to go exactly through the data, everywhere. OK. Oh, yeah, good old k-nearest neighbors. So it turns out k-nearest neighbors is actually, it's a simple idea, right? I just take some new point, I find the k-nearest neighbors in the data, and I look at the prediction labels y in those points, and I use those prediction labels in some combination to infer a prediction label for this new point. But you can express k-nearest neighbors as just a special case of local basis functions. I just have some funny little similarity function, which is 0, 1. It's 1 if you're a kth nearest neighbor, and it's 0 if you're not. Right? And then you expand out, so here's a little graph, and you expand it out into a new feature vector. The new feature vectors are Boolean, 0, 1 vectors. As long as this new matrix you create happens to be full rank, not guaranteed. In fact, you need k to be not too big, not too small, but if it's full rank, you could interpolate. And so on. OK. All right, so last thing I am going to say about sort of this mundane view of feature expansions is none of this really requires the input objects x to be vectors. Okay, so here's the first empowerment, right? If your domain is documents, or maybe your domain is sentences, or strings, or DNA sequences, feature vectors aren't yelling out at you as the natural way to represent the problem. The natural way to represent the problem, say, is in terms of strings or structures or graphs, labeled graphs. Okay? Nevertheless, you can still treat such objects in a linear framework simply by the same mechanism of designing feature functions over those objects, right? So over a string, I can certainly have feature functions that like count n-grams, like how many times does this pattern appear in the string, right? And that would just be a feature, one dimension in my re-representation, right? So the game is you can take these other arbitrary structures and map them into some vector, finite dimensional vector space, okay? I'm not even trying to say this is a good idea or a bad idea. It's an idea, but if you do this for free, you get all of the algorithmic technologies that we've developed, right, for solving linear systems. And in fact, you're going to get more than that. We're going to get all the things that I haven't talked about yet, okay? So even though this seems like a very unnatural way to approach problems like this, say in the field of natural language processing, no doubt some of you are in, you would know that it is dominated largely, more than it should be, by linear function learning techniques, where you're taking sentences, literally strings, and then re-expressing them as feature vectors over n-grams and other features of strings, and then just applying linear modeling on top of those. So this is a very flexible way of looking at modeling data, right? Just map it into some finite dimensional feature space. Go from there, okay. But of course, in practice, this is where all the action is, right? If you're in image processing or video processing and so on, understanding what are the important things to extract from the data is what the field is about to a large extent, right? And some machine learning guy isn't going to be able to go in and really tell you effectively what features you should be using in image processing, right? That's domain expertise. Same thing in natural language processing, couple decades of experience now of understanding what's important to measure in a sentence to infer things about syntactic structure, okay? So, I gave you this generic view of feature expansions, but really in application, this is where the action is. You have to, deploy understanding in choosing features that you think are meaningful features for the prediction problems that you're faced with, right? If you're just adding random junk, garbage in, garbage out. Although I'll show you, random features aren't a bad idea. But okay. So that's what's going on in application areas. Even in application areas, some of these generic techniques do get deployed, and they do sometimes help. Okay, the elephant in the room. All right. What am I not talking about that everyone knows I should be talking about? Well, overfitting. So, here's sort of the intuitive way to think of it. So, I get hired at Google, and they sit me down, and they say, solve this, image recognition problem, okay? And then, it's like, oh, I don't know what features to use. If you don't know what features to use, what are you thinking? Well, why not use all the features? I should just use all of them, right? Can't go wrong. That way I can model anything. But of course, that doesn't work. That's not what this game is about, right? If you use all of the features, you'd better have all of the data, and maybe even more than that, right? Because machine learning isn't just about making models and solving optimization problems. It's about making models, extracting them from data, and having them actually work on new data, right? So we get this very natural tension, right, in practice, this dilemma between underfitting or overfitting. So we want to minimize the number of features to avoid overfitting. I'm still speaking very intuitively about this, okay? On the other hand, we want to maximize the number of features we're using to make sure we haven't left out the key feature that really unlocks, how you get predictive structures in this domain, okay? And how do you sort out this, little conundrum between too many, too few, which features, okay? It ain't easy. In fact, this is sort of one of the core, fundamental problems that machine learning and statistics and related fields really, think hard about, okay? I just can't help but, show the usual demo. You have to see at least once in your life. If you've seen it before, you should still see it again. What happens if you add too many features? Well, it doesn't work the way you think. So you think oh, I'm going to add all these features. I'm going to model the data better and better and better. Well, that's true and not true, okay? Just, observe what happens. So we look at our simple, step function sampled thing. And this line here, was my amazingly computed best constant fit to that data. Okay? So that's my polynomial that uses a single feature, the feature 1. Okay, so not a very inspired model of that data. And we can see all kinds of prediction errors. However, it's got something really good about it. So it's got these fairly big prediction errors, so it's clearly underfitting. Okay? Underfitting is good. What do I mean? Underfitting is good in the following sense. If you're underfitting, you know it. This is great, right? I'm underfitting the data. Okay? I need more features. So you go out and you say, OK, let's get more features. Like I'll add a linear feature. Still not that inspiring, but I feel like, yes, we're modeling the data. Okay? Let's add a quadratic feature. Actually, you didn't see it, but there's a slight bow. Anyway, cubic. Now we're thinking, this is going to work, right? Just keep piling on those features. We're going to start modeling that data. And indeed, our prediction errors are getting smaller. Okay? Quartic, quintic, 6th order, 7th order, 8th, 9th. So something's going on. It's sort of like it's kind of working, and then it's really catastrophically not working. Yeah? OK, 10. Anyway, you might as well see 11. Ooh. One thing to note, right? Adding features isn't like continuous in the solutions that you get, right? You get these dramatic tail flops, for example. What was that, 12, 13, 14? You can see sort of regions where this is starting to maybe do something, and then you can see things aren't good. And if you just keep going, what we're really just seeing is amazing instability all the way up to the final fit, right? 20 data points, 19th degree polynomial, perfect model through every single data point. Okay? This is just it's going to predict amazingly well on new data from that distribution. Okay? This is overfitting, obviously. Overfitting is a killer. Why? Because you can't see it, right? What are you seeing? The only thing you're seeing is 0 prediction error on that data, right? So if you look at this, this simple toy sequence of models, we make the models richer and richer and richer. What's happening? The training error, the prediction error you're seeing on training data, monotonically decreases. It's going to monotonically decrease because we were clever enough to set up optimization problems we could actually solve. And so when we actually solve them, we're going to see the prediction errors monotonically decrease. Okay? So the underfitting problem, we're going to see disappearing before our very eyes. What we're not seeing is the generalization error, the true test prediction, the expected test predictions that's going on in the background off of that training data. Okay? Overfitting is insidious because you can't see it. A couple of just intuitions, though, to help us out. It's very easy to understand what overfitting looks like, especially in this kind of catastrophic-looking setting. The thing you notice about these polynomials is they're wildly unstable. So if you look at something like this, if I take these data points, and I take one of those data points and I just wiggle it a little tiny bit, I forgot to make the plot, but if you wiggle one data point a little tiny bit, that polynomial is just going to flop around like mad. Okay? Here's another way to look at it. Don't even change the data. Same data, okay? But I can have other 19th degree polynomials that do exactly the opposite. Instead of shooting down here, it shoots up here, shoots up there, and it almost goes through all the data. What is this telling you? In the space of functions that you're representing, you have completely, wildly different functions that all look about the same on the training data. You know that's a problem, okay? And in fact, intuitions like this are pretty naive, but actually they go a long way to understanding how you're going to combat overfitting. Okay? So modeling and computation are important, but of course to combat overfitting or to get good generalization, there's this other elephant in the room. We have to understand how to control the complexity of the models that we're fitting to the data somehow. Okay? Now I confess, I'm not going to have time really in my lectures to go into generalization theory and how we could provably relate training error to expected test errors. Such things exist. Well developed in some senses, not so well developed in other senses. I'm hoping and expecting that other lecturers will dive into some details about generalization theory. I could do something if I had to. Okay, so last sort of large topic, but it still leads to many generalizations, just as a happy side effect. I'm going to just talk a little bit about strategies for combating overfitting. I'm not doing this in a deep way. I'm just going to talk about sort of the generic basic approaches that people use algorithmically. Essentially, we have this dilemma, too few features. We underfit too many. We overfit. How are we going to combat it? There's sort of two generic computational approaches to this problem, or the way it renders out computationally. I'll come back to Bayes later. But in this kind of optimization setting, we have feature selection. That is, given this massive set of basis functions, wouldn't it be grand if we could just reach in and pick out a small, meaningful set and just avoid overfitting, but still have a good enough small set of features that we also avoid underfitting, okay? So we could try to use some feature selection process to both choose the features and learn the model on top. Computationally catastrophic, but sounds like a nice idea, okay? A related but different idea is not to actually choose features, okay? Is to keep them all, but to smooth the weights. That is, bound the slope of the function, because if the function's 0, we certainly can't overfit. And if we just kind of keep it close to 0, we're going to keep the overfitting under control. And if we have enough magical features lying around, even if they have small weights, that's going to be good enough. This is the idea, okay? Regularization. The nice thing about regularization is that, if done the way we're going to do it, it's tractable, right? So it's going to be just a trivial thing to bolt on to empirical error minimization. There's going to be a little knob, right? But it's computationally attractive. It doesn't get in the way at all, okay? Amazingly, it does more than that. If we just start to look a little bit at regularization, there's this astonishing accident, which is particular forms of regularization lead to this shocking generalization of finite dimensional feature representations, kernels, which you know about, but I'll drag you through it anyway, okay? And the other sort of popular exploitation of regularization is to realize that if we start using particular regularizers that lead to sparse solutions, that is, zero out a lot of the weights, that is implicitly like a form of feature selection that is still tractable. And that also has been a pretty useful, at least computational technique, even recently. OK, so here's sort of my mini plan for the next little stretch, is I'm going to talk about regularizers. Okay, so no more feature expansions, but just talking about complexity control just from this very simple perspective of regularization. Okay, the committed Bayesians are really angry with me right now. I'm an agnostic. I don't, okay, Bayes is fine if you can do it. Okay, but I'll say more about that tomorrow. Okay, so for now I'm just going to talk a bit about regularizers. Okay. Regularization strategy number 1, Euclidean regularization. So I poo-pooed Euclidean geometry in the loss function, but I didn't mean to do that. Euclidean geometry is both beautiful and, as we'll see, powerful. Okay? The point is, though, is that you don't want to hamstring yourself by imposing Euclidean geometry in the loss function necessarily. It doesn't need to be in the loss function. Where you need Euclidean geometry is in the regularizer. OK, so complexity control via regularization. So strategy number 1 is we're going to just add this little thing to our empirical error minimization, just a little penalty on the magnitude of the weights. OK, and here I say Euclidean because I'm going to take the L2 norm squared, the Euclidean norm. And I'm just going to penalize or measure the magnitude of the weights by the Euclidean norm. This is spherically symmetric, right? It just says the length of the weight vector is how I'm going to penalize it, right? If the weight vector is 0, 0 penalty, right? And if it's really long, there's a big penalty. And then I've got a little knob here, beta. OK, knobs are bad. I agree. Hopefully somebody will say something about tuning knobs, OK? Anyway, I got some knob beta. If beta is 0, it's just empirical error minimization. And as beta grows, there's effectively a bigger constraint or smaller constraint on W. So we could think of beta as a Lagrange multiplier, and we could literally be thinking of this as a constraint on the magnitude of the weight vector, or equivalently just a penalty. Okay, they're going to be convertible to one another. OK, So initially, we look at, say, the Euclidean regularizer, and we think like, well, that's a fine choice, but it's not special in any way. You know, we could use any other norm. We could use L1 norm. We could use LP norms. Why even a norm? We could just have some measure, okay? Fine, but we start looking at Euclidean and we say, well, here's some nice things. It's convex. Oh yeah, we probably want it to be convex, right? At the very least, or we're going to lose tractability of training. This one is smooth. That means we have a gradient, and the gradient's really simple. It's just a linear function of the data. Has almost no impact on the computational procedures. If you're doing least squares here, this is like just a small, spectral shift of the matrix in the normal equations, whatever. Okay, but none of that matters, right? There's just many ways you can measure length and tune knobs and get it to avoid overfitting. It just turns out Euclidean geometry does something magical and special that is important to understand because it is a strict generalization of what I've shown you so far in terms of finite feature representations. Okay, and that is. Euclidean regularization has nothing to do with the loss function. The regularizer gives us reproducing kernel Hilbert spaces. Okay, so let me just take you through this. And now I think most people, everyone's learned about kernels. 90% of you learn about it in the context of support vector machines, but it has nothing to do with support vector machines. When you think support vector machines, you're looking at like, this margin hinge loss thing. It has nothing to do with that. It's just that little Euclidean regularizer attached to it, okay? Kernels apply to everything as long as you have Euclidean regularization. I'm going to overemphasize this point, but I think it's an important misunderstanding to avoid. Okay, so so see, I can add a Euclidean regularizer to my 19th degree polynomial, and if I tune the knob, I get it to kind of, well, not go crazy. Okay, here's the important thing about Euclidean regularization is the representer theorem. Now, this isn't the representer theorem in big, bold letters. This is a very simple property. In fact, it's a trivial consequence of linear algebra that leads to the power that we're going to pull out of this. So take any loss function. It doesn't even have to be convex. In fact, the loss function is not important. Just some function, okay? And then I'm going to add a function to that, and then I can even generalize. I'm going to add any increasing function of the Euclidean norm, okay? And so I'm going to have some penalized optimization with just any increasing function of the Euclidean norm, and I'm going to solve it. If the solution exists, like, if I haven't picked some crazy loss function that there's no solution, if the solution exists at all, then it's guaranteed that that solution can be expressed as a linear combination of the training vectors, okay? Now, this sounds silly to make a big deal out of this. Okay, fine, so what? This has real consequences, really important consequences. And it's a trivial fact of just using Euclidean regularization. In fact, it's so trivial, this is the whole proof. I might as well show it to you. I'm not going to show proofs, but this one's just so easy, anyone can get it, okay? Why is it the case that if I solve this problem, the solution is guaranteed to be a linear combination of the data, the original feature vectors? Well, it's not hard. Just think, look at any vector. Well, we could look at the optimum vector, but take any vector. Any vector, right, can be rewritten as a sum of two vectors, one in the row span. That is, this is a linear combination of the data. And then another vector that is orthogonal to that row span, right? So we can just rewrite any vector as spanned by the data, orthogonal to the data. Fine. Well, look at this loss, right? The only way that weight vector participates in the loss is linearly in phi. But if I decompose W into the W0 and W1, the phi W0, well, W0 is orthogonal to phi by construction. That's 0, right? So the W0 doesn't affect the predictions. So you don't need the orthogonal component to do anything about the predictions on the data, okay? So forget about the orthogonal, you don't need it for prediction. Well, the only other thing the orthogonal component could impact is the regularizer, and this is where things get focused, okay? What happens on the regularizer? What was so special about Euclidean? Well, the Euclidean norm, right, if I look at the sum of these two things, W0 and W1 are orthogonal. That's what's special about Euclidean, the Pythagorean theorem, right? The sum square, the hypotenuse squared is the sum of the two squares, okay? Which means it additively decomposes into the sum of these two things. If this W0 term is not 0, Well, then we get a contradiction, because then I can write the original combined objective as only depending on W1 here, and then depending on the sum of these two things, R is increasing. So if R is increasing, this is strictly smaller by dropping the W0. So the only thing you can do by having anything on the orthogonal component is make it worse. Therefore, it's 0. If it's 0, it means the solution is just writable as a linear combination of the data. Blah. OK, so yeah, math class, sorry. It was trivial. I know it was boring, but it was easy. There's no functional analysis here. There's nothing deep. This is just first-year linear algebra, right? OK, this first-year linear algebra has profound consequences. Okay, so just simply because the solution, because of the Euclidean regularization, can be written as a linear combination of the data, well, now we get equivalent reformulations of the training and prediction problems. So here's our original problem. So I go back to the Euclidean regularizer squared. Sorry, I changed my notation. So this is my original training problem. Here's my original predictor. Well, since the W could be expressed as a linear combination of the data, I could just rewrite the optimization as over this adjoint weight vector. So instead of the weight vector on the features, I can just replace it with a weight vector on the examples. Okay? And so now I'm going to learn a weight vector on examples. And then I'm just going to replace W with the phi transpose A. That's what we saw on the last slide. Okay? And I'm going to make that substitution everywhere. And I get this training problem. So this looks crazy. You probably haven't seen it before. But it's an arbitrary loss, still linear. This is still linear in A, so it's still convex. Yeah? And then I've got that thing there, okay, which is a convex quadratic in A. So computationally, I've lost nothing. Okay, well, okay, I may have more weights that I'm optimizing, but I've still got a tractable, say, convex problem if I had one to begin with. And I could re-express the prediction in terms of the adjoint weights. So here's the other thing. You don't need the weight vector on the features. Now, I know you may want it, okay, but it turns out you don't need it. You don't need it for training. And you don't need it for prediction. In fact, you would never need to look at the weights, W, right? You could do the entire process strictly in terms of the weights A, any loss function, okay, and still get a linear predictor, okay? And so here's this little observation you've all seen before, but I'll just re-emphasize it. If we look at this bizarre-looking equivalent adjoint formulation of the problem, what do we see about the feature representation? Well, we see this outer product matrix, the phi transpose matrix, which is a matrix of, well, it looks like an outer product, but it's the matrix of inner products between the feature vectors, right? And then if we look at this predictor is a matrix vector multiply. So this is the feature representation of the test point, and that's the big matrix. This font sucks. Anyway, that is a vector of inner products between the feature representation on test and a feature representation of a training example. Okay? You don't need the features. You don't need the weights on the features. You could do it all with just weights on examples and inner products between feature vectors. Okay? Nothing deep. Okay, but that's profound. So we could just replace all of these inner products between feature vectors with just some compiled function, say kappa again, which just computes that inner product directly. Okay? Maybe I'll skip to this down here. Having, a function that can compute inner products directly, by the way, is a huge thing, even computationally. So computer scientists like this, if I have, say, like this, just a demo, I have this big, long polynomial feature expansion. So, we have these polynomial feature expansions. But say, for some reason I want to go up to D 100th degree polynomials, right? Fine. Or 1,000 or 1,000,000, whatever. These messy-looking things are just coefficients. You can see I've just kind of engineered it. Okay? How would you compute inner products between feature vectors like this? Well, you might think naively like, well, I have to write a loop. I have to loop over all the features, and then I have to take multiplies and adds through the whole thing. The computational complexity is order D, where D is the number of features. But that's daft, right? For this feature expansion, of course, there's a compiled version of that inner product, which is simply this computation. If I want the inner product between x1 expanded and an x2 expanded, it turns out it's just x1 times x2 plus 1 raised to the d, right? Constant time computation. So you can compute the inner product without a loop, okay? This is, okay, this sounds boring, like, okay, fine, you know, you shrink a loop a bit. What happens if that feature vector is infinite? Okay, that sounds crazy, but you know that's coming. If that feature vector is infinite, going from infinite to constant, you know, that's not bad, right? So, you know, this is a good idea, you know, trying to compile or think about features, recognizing that all we really need to care about, perhaps, is just inner products, and then understanding, can we take the feature representation you're working with and compile it into a direct inner product computer? If you get an efficient, you know, nice algorithm for the inner product, this is a huge computational saving, perhaps an infinite computational saving, okay? And so this is just rewriting the previous thing. You know, I could just, that phi transpose, I could just rewrite as a big matrix K, where each entry in K I compute by just calling the kappa. Yeah? And so we can express training as a convex optimization on the adjoint variables with respect to the kernel matrix. And prediction can be expressed as, again, just a linear predictor with respect to the kernel vector, the vector of inner products between the test feature vector and the training feature vectors. Okay. Now, this is kind of the cool step, right? Is to recognize that you don't need the feature vectors, and in fact, we could work with the kernel. And once you recognize that, you realize, well, forget about feature vectors, right? You could start with the kernel. So you don't have to engineer things the way I've been kind of portraying it so far, where you sit down, you look at your application, your image processing, your language processing application, and you think hard about features, okay? While you could instead think hard about similarity measures, kernels, okay? And I'm sure you all recognize that this is a large part of what goes on now, is thinking in terms of kernel representations for applications as opposed to just strictly feature representations. However, it's a little bit tricky, right? So what is a kernel? So a kernel is going to be a function of two arguments, real valued, that is symmetric. So it's a symmetric function, and semi-definite. And semi-definite is a technical condition, but it's easy to state. It simply says that the kernel takes two arguments from some domain X. It's a semi-definite function if you take any finite set of objects and you build the kernel matrix, that is the square matrix of all the similarities computed by kappa, and you build that matrix, and if that matrix happens to be, well, it's guaranteed symmetric, because the function's symmetric, but if in addition to being symmetric, it's positive semi-definite, that is all of the eigenvalues are non-negative, then this is guaranteed to correspond to some implicit feature representation, and therefore can be applied in the previous setting. So any positive semi-definite symmetric function corresponds to some feature representation. The cool part is that you just reach into your bag and pull out like a kernel function. So for example, the one we saw before, the Gaussian kernel, I didn't verify then, and I haven't verified now, that this is in fact, well, you know it's symmetric, but it is in fact a semi-definite function, okay? It's not hard to prove, anyway. This semi-definite function is a kernel. It's the default kernel. It has nice properties. It's in fact a universal kernel. But this kernel has no finite dimensional feature representation that corresponds to it, right? It actually corresponds to an infinite dimensional representation. And yet, if we solve the training and prediction problems in the kernel space or in the adjoint formulation, it's all finite computation, right? The implicit, infinite dimensional features are just compiled away in the inner products that are directly computed by the kernel, okay? So in this sense, this is not a trivial extension. This is a powerful extension, right? This is telling us that we don't have to think about finite sets of features. We can, in fact, think about infinite sets of features, and we can still have tractable, finitely computable solutions, both for training and prediction, over infinite feature representations, okay? So, okay, fine, that was cool. The problem is to work with these particular infinite dimensional feature representations is you have to be able to now think in terms of kernels and be able to verify that you have positive semi-definite kernels. And if you don't, you run into problems because you lose tractability in the training and so on, okay? So it's a bit awkward, but it's look, it's cool, and it does feel empowering, and it has really worked in many different applications, okay? Now, I don't look at feature expansions or kernels as an either-or thing. I think the point I'm trying to make is, in terms of modeling flexibility, this is another powerful tool to be aware of, right, when you're tackling a problem, okay? Okay. I think I'll skip this. So normally when you learn about kernels, and it's a fine thing, you first have to learn about functional analysis. Actually, we got this far with elementary linear algebra, but fine. There is some really beautiful functional analysis that has already worked out a lot of things about reproducing kernel Hilbert spaces. All this slide is saying is that there's a construction. Essentially, there's a proof that if you take any positive semi-definite kernel, then you can induce an implicit feature representation. That is, there is a Hilbert space, which is infinite dimensional feature representation or inner product space that corresponds to that kernel. And so for any positive semi-definite kernel, you can construct a coherent, well-defined Hilbert space that kernel represents the inner product for, okay? And it's, a cool exercise. Actually, what's kind of maybe important about that is that there is the real representative theorem. The real representative theorem isn't what I've shown you already, which is just a trivial statement about linear algebra. The real representative theorem is a trivial statement about functional analysis, okay? But it basically says the same thing, that if I have a space of functions now described in this implicit feature representation, and I have the same kind of optimization problem expressed there, where this notation just means the same kind of like Euclidean norm in that Hilbert space, then it turns out the solution can always be rewritten as a linear combination of the implicit features, where the implicit features are expressed in terms of the kernel similarity function. Okay. Sorry, just give me a sec. Actually, I'm really distressed that I'm talking fast enough, because it takes longer to make the slides than to show the slides. I might just, I don't know, I might take one more topic and then slow down. Actually, it also means I'm probably, well, I can't tell. I'm probably talking too fast. Many of you teach, okay? So you know what I'm about to describe. When you look at a classroom, everything looks the same, right? Everyone's blank, right? What does that mean? Well, they're lost, it's boring, or it's easy, or too hard. It's really hard to calibrate. So if you're really annoyed, any kind of signal like speed up or slow down.
Maybe you want to take some time to take questions.
Yeah, I don't see any questions. See? That's okay. I'll cover one more topic. Okay. And again, as you can tell, I'm being somewhat cursory, and I'm just trying to give you an overview. Okay, feature selection. So this is let's step back. Okay, so Euclidean regularization, Euclidean geometry, Hilbert spaces, fun stuff. Okay, beautiful and even useful and powerful. But let's just go back to feature selection. Okay. So here the idea wasn't to smooth out weights. It was backslash. Anyway, is to choose a subset of the features. Okay, literally, look into our set of features, maybe infinite, probably not, and just try to pick some best subset. And I've mentioned this already, but subset selection is hard. Well, it looks hard, naively. There's an exponential number of subsets of any given size. That's not good, so you can't enumerate for any reasonable size. But it's actually been, shown to be, literally, as far as we know about the hardness of computation, this would be one of those hard problems. Okay. So feature selection is hard. Now, recently, people have, I guess, rediscovered that, when faced with a difficult combinatorial optimization problem, relax, okay? And then at least, get something that you can solve quickly and then try to patch it up later by showing how close you were or something, okay? So in the context of feature selection, a different regularizer has sort of wound up being, I think, currently perceived as a predominant approach. Now, again, I feel like I'm just the messenger. I'm not really trying to sell this. But in the literature right now, there's a lot of emphasis on what are called sparse regularizers. In the context we're in so far, this would amount to just using an L1 regularizer, which would be like a convex relaxation of feature selection in a sense that I haven't explained yet. First, let me just go back to the computational problem. So we go back and we get rid of the Euclidean regularizer, and we just bolt on instead L1, the sum of the absolute values of the weights. And so now we're no longer penalizing weight vectors by their length. We're penalizing them by, well, their length in this other, in a Borel space, like in L1, so the diamond unit ball, right? OK, fine. And we still have our little knob that has to be set. Has some notable properties. One is that it's still convex. So the L1 norm is a convex function. In fact, any norm, almost by its definition, if you look at it, is a convex function of the argument. Okay. Happens to be non-smooth. And that non-smoothness here is important. In fact, that non-smoothness here is what's kind of giving us this approximation of feature selection. And so I didn't write a slide on this, but this is a convex lower bound of a feature selection cost, or an L0 norm, in a certain way that I think isn't that deep. But anyway. OK, so it turns out that if, again, nothing to do with the loss, just the regularizer. We go from a Euclidean regularizer to an L1 regularizer, and it's almost like the universe has changed. So we go from L2 to L1. All that stuff about Euclidean geometry, Hilbert spaces, kernels, all gone. It's gone. By the way, I forgot, go back. That was the reason we had kernels, right? The representer theorem was because of this part, not because of that part, right? And I've changed it to L1. It blocks the representer theorem. There is no representer theorem here. So that means you cannot solve this equally by just replacing weights on features with weights on data. We have to be stuck now with weights on features, or so it'll seem. Okay. Yeah. So kind of a dramatic step, but I'll bring the two together tomorrow. Okay. But for today, why is this so dramatically different? Well, we can look at the plot of the L1 norm, and we can see that it's this pointy thing here, and this non-smoothness is the reason why we get sparsity. Now, I'm going to just try to give you the intuition, if you don't know it, is, OK, so I have this penalty on a weight, right? In fact, the L1 norm is just the sum of these weight penalties, the individual weight penalties, OK? And then if I look at the gradient, well, I can't really look at the gradient here because it's undefined. But if I look at the gradient over here, it's constant. It's a +1 gradient, +1 derivative, right? If I look at the derivative over here, it's -1. And then it's undefined there. And that's important. So in terms of optimization and in terms of understanding these things, we have to generalize our concept of what a gradient is to cases like this where we don't have differentiability. In fact, we don't have differentiability right at the point we care about. Okay? Other people will talk about this more deeply and I think maybe more intuitively. But just quickly, what's a gradient, right? Well, in a one-dimensional function, what's a derivative? It's just a number, okay? Or a gradient is just another vector in the same space as the input argument, okay? That it just is the slope and orientation of the supporting hyperplane. So the gradient at some point is just the slope and orientation of a supporting hyperplane, right? It's the linear function that supports the function there, right? Okay. Now, clearly, if we have a point that's not differentiable, it turns out that the number of supporting hyperplanes is, it's infinite, right? That you have this whole family of supporting hyperplanes. Each one of these is what we call a subgradient. Okay. Now, if the subgradient is unique, well, then that would correspond to a gradient, and we have a differentiable point, right? If the subgradient is not unique, then we have a whole family of supporting hyperplanes. Okay. Now, in a minimization context, in a differentiable case, right, we're all interested in the zero vector, right, the zero gradient vector, which means the function's flat, we're at a local minimum. In this kind of context, you will never find that zero vector, right, because at the minimum, there's a whole family of vectors. Okay. What's important in an optimization context is just that the zero vector is one of the supporting hyperplanes. okay? But if you call a subroutine to say, give me a subgradient, any old subgradient, it may just say, okay, there's one, right? Or there's one. And the task of determining that you're at a minimum is non-trivial, right? Because you have to somehow explore the set of subgradients at your point and understand if it's got the zero vector in it. Okay, anyway, I'm not going to sort of dwell on this from an optimization perspective, but from a sparsity-inducing perspective, we can see that that non-differentiable point at 0 is why we get sparsity. So why would we, if we're trying to do like sort of a quasi-gradient descent like optimization, why is it that if we have some weights at 0, that they're going to stay at 0? Okay. Well, we could think of it as just like a game, right? Opposing pressures. So just naively, like think of the gradient. Okay. Now the gradient isn't defined at 0, but think of a gradient away from 0. What would we be seeing? We'd be seeing two terms, right? This is the term coming from the regularization penalty. This term is trying to drive the weight back to 0. And it's trying to drive it back to 0 with a constant pressure, you could think of it, right? And then this term is the gradient of the loss. So this is the term that's driving the weight to try to minimize the loss, okay? Now, the gradient, of course, is just this vector of these partials. So just look at one of the partials. What happens if you have at a current sort of position in the weight vector space, one of the weights happens to be 0, okay? And then just look at the partial derivative, like the gradient entry on that weight, right? Is it going to want to move? Well, of course, it's at 0, which means there is no gradient here. But we know that it's caught at this corner, right? So anywhere that it moves, if it tries to go bigger, immediately it's got a -1, right? If it tries to go smaller, immediately it has a +1. So there's this constant ±1 pressure trying to keep it at 0, okay, multiplied by beta, okay? And what's countering that pressure? What's countering the pressure is the loss minimization on the data. The absolute value of this term here, that's the partial derivative of the data, like the loss on the data. So this is the term that's trying to drive the weight to reduce training error. And this is the term that's trying to drive the weight to keep it at 0, okay? And basically, it's just a simple competition. If this pressure trying to keep it at 0 is greater than the magnitude of this derivative term that's trying to drive it away from 0, then you stay stuck at 0. Very non-technical description, right? But sort of very clear why this non-differentiable point is important because it's non-differentiable, right? Think about the least squares. As you get closer to 0, it flattens out, right? So it'll never keep you at 0. You've always got a little bit of a compromise between this pressure, which gets weaker and weaker as you get to 0, and the loss minimizer, okay? So you make it sharp, a lot of the weights go to 0. As you increase beta, obviously, the only thing that can happen is weights get smaller and more weights get stuck at 0. Right? So beta now is like your feature selection like knob. I'm not trying to sell this, it's just the way it works, right? Some feature selection like knob, if you make it bigger, makes the solution sparser, make it smaller, gets less sparse. Now, what this has going for it is that once you've at least set the knob, all the training is still tractable, assuming the original loss minimization was tractable. Oh, yeah, that's all this is saying. So, there are various ways you could go about this, but just if I just have bolt on an L1 regularizer, I could always just re-express it, for example, as a convex constrained optimization. I'm not saying that's the way you really want to do it necessarily, but it's easy to formulate optimization problems of this form into various tractable forms. Okay. I think this is where I'm going to wrap up. Okay, so like I described before, here's where I'm going to leave you. I guess it's like the last episode of the season. Okay, I'm going to try to leave you hanging. I've shown you two ways to regularize the weights using Euclidean geometry, Euclidean regularization, which leads to Euclidean geometry, Hilbert spaces, kernels. Seem nice. Then I stepped back and said, well, okay, let's try L1 regularization because that's going to give us like an implicit form of feature selection. Seems okay. Why wouldn't we want to put those together, right? Like, why wouldn't I want to now both select features in a kernel setting, right? And we'll see that that really is coherent, that we could think of kernel selection as decomposing a kernel in terms of a bunch of little kernels defined, say, by features or sets of features, okay? And trying to keep kernels with some Euclidean regularization, but still introduce feature selection or kernel selection, right? Using L1 regularization to drop out some useless kernels or features, okay? It's a natural thing to do. It's sort of an obvious thing that people thought of, but it's problematic. It's problematic because of what I said before, is that the moment I introduce this L1 norm, we actually lose the representer theorem, which means we lose kernels. That is, we cannot equivalently write a problem with this regularizer as a kernelized problem in an adjoint form, okay? So what are we going to do here? Well, it turns out there definitely are techniques for combining these things, but they're not just a naive approach. I just bolt on some knob in an L1 and some other knob in an L2. It actually requires a little bit of work, okay? But it's not that deep, but it's sort of interesting. The way we can combine these is with a little bit of indirection. So what I'll start showing you next time, before I go on to other generalizations, is how we can do kernel selection, combining L1 and L2, with a bit of a cheat. What we'll do is we'll introduce a new auxiliary set of variables, which are feature selection variables. So we'll have two sets of variables on the features. We'll have the original weights on features, and we'll have a new parallel set of weights on features, which are meant to be feature selection variables that go to 0 and remove features, but aren't really supposed to be modeling the data. It's a bit dicey, okay? But we'll take this trick, and then what we'll do is we'll regularize the original weights with Euclidean, which means we'll still get representer theorem with respect to those weights, and we'll still get kernels. But now we have these auxiliary weights, which are separate, and they won't block the representer theorem. But we'll be able to do L1 regularization on the auxiliary weights without blocking the kernel on the original weights. And we'll get some rickety form of combined feature selection and weight training. Now, it turns out you can do this. You can do this tractably, closed form global optimization. Not closed form, but globally, global optimization. But it actually isn't that easy. We have to do some fancy reformulations, in particular using Fonchel conjugates of the loss functions and so on. But I'll sketch out sort of next time how we can combine these and coherently do selection and kernels together, and then show other generalizations. I'm done. No questions? All right, so it was boring class, I guess.
When you exit the room, you go to the main hall, take left all the way down, the staircase is going to be there. Yep. Exit the room in that direction, it's going to be a walkway towards left. Tap out.
News they talked about, are they going to be